Okay, here's another one. Now this one, um, remember we worked with this thing. We worked with something like it was back a while ago. We had like 2 to the k. No, I take that back. We had like 2 to the n, and we had n factorial like that. Um, and we saw that this thing actually did converge. That n factorial is very large when this number is constant in the base. So the n factorial overpowers it in a sense as n gets large. So that eventually all the terms, except for the first several factors, are definitely less than 1. And then you have a bit of a way of showing that. But this one, I kind of suspect that n factorial is not going to be able to catch up with the n here, because I mean, just logically, you would think this product n factorial is, for example, let's say 6. When n is 6, we have 6, 5, 4, 3, 2, and 1 product, for example. And then in the denominator, you have 6, 6, 6, 6, 6. Every single factor here in that denominator is at least as big as the numerator. And most of them are bigger. The only one that's not is this one. And that's a 1. The rest of these are all less than 1. So this is a single product in here. And it's less than 1, basically for all n. We might be able to say that that's not true for, say, n equals 1. When n equals 1, you just have this. Okay, so that first term tossed out. For n equals 2, you would have 2 times 1 over 2 times 1, like that. Sorry, 2 times 2. So the second term would be less than 1. So if we tossed out the first term, we'd have each of these terms that followed. The next one would be 3, 2, 1, and then 3, 3, 3. So you can see how each term is going to be less than 1, every term. So it looks like these fractions, these terms, are heading to 0, and that so we suspect there might be some convergence if they head to 0 fast enough. We know heading to 0 alone isn't enough, but we can't say that they're not heading to 0. Let's put it that way, so that it would be divergent. We couldn't say that. So we suspect that this thing's going to converge, but let's go ahead and go through the math to determine this. You set up your R, and it's this limit as n goes to infinity. And I'm going to just go right in here and set this up, n plus 1 factorial over the n plus 1 to the n plus 1. And then it'll be times, we'll have n to the n and an n factorial underneath. So, and you can ignore the absolute values because they're not, this is a positive term, all of this is positive. Okay, so now let's see where this takes us. And the limit n is going to infinity. Let's break this up. N plus 1 is an n factorial, and then you have an n to the n. And down here you have an n plus 1. And then you have an n plus 1 to the n. and then you have an n factorial. Okay, so I broke that up. I can reduce some of this stuff now. Let's see. We'll be able to get rid of that with that, and that will go with that. And so it looks like we just have this left over. N goes to infinity. We have an n to the n, or n plus 1 to the n. Okay, that's a little bit small there. Okay, now let's see what happens here. This is the limit. N goes to infinity, n over n plus 1 to the n. And still, looks like it's heading to a 1. But 1 to the infinity is not, it's indeterminate. So the inside's heading to 1, but we have infinity out here, so that's an indeterminate form, 1 to the infinity. So we'll have to do a little more. Let me just take it over here on the side. I'm going to divide like this. We have a 1 and a 1, or an n plus 1. So I have a minus 1 here. So back down here we have a limit n going to infinity of 1 minus 1 over n plus 1 to the n. Okay, so that really doesn't help us much because we still have the same thing. We have the inside heading to 1 and this exponent heading to infinity. So that doesn't help. So at some point, maybe even at this point, you might say we could use our log form. We'll take the natural log of r. And because we have composition here of a continuous function with a continuous function, we can write this as, let's see, the limit n goes to infinity, and we're going to write that as n. Why that keeps popping up? N y natural log of it'll be the n over n plus 1 like that. Okay, and that's equal to this limit. Natural log of n over n plus 1 with a 1 over n like that. So what we have is this function up here. N's going to infinity, so this becomes natural log of 1, which is a 0. And this is heading to 0. So you can use L'Hopital's rule on this now. Assuming n is a continuous variable. If it works for the continuous variable, it'll be the same limit for the discrete in this case. Now, okay, so we need our derivative. Let's see, we want the derivative of that, so that's going to be kind of messy. Let's say it'll be n plus 1 because that's the derivative of numerator times the denominator, and then minus another n over n plus 1 squared. And then that itself is divided by n over n plus 1. And then all of that is over the negative 1 over n squared. That's the derivative of this 1 over n. So let's see where this takes us. Um, let's see, this will be a 1 up here, so we have a 1 over n plus 1 squared from here. And then this is n over n plus 1. So it'll be times n plus 1 over n. And then this will be over here times another negative n squared. Okay, so that numerator and that denominator. So all of this becomes, let's see, we've got a negative n over an n plus 1. And that limit is negative 1. So what we see here is that we have the natural log of r equals negative 1. So e to the negative 1 equals r. R equals 1 over e, which is less than 1. Therefore, we have absolutely convergent. Okay. And when we say absolutely, we don't mean it in a nonchalant way. Like some people would say, absolutely. No. Absolutely in this case does mean that we have this series would converge. It's absolutely convergent. Okay.